Well, our last speaker for today is Hector Benitez, and he will speak on deformation of AES5 plus S5 pure spinor superstring.
Thank you. Many thanks to the organizers for inviting me. I'm very happy to be here to talk about my PhD work. This work was supervised by Victor Riveles. He's my PhD advisor. So this work is about the eta deformation of the ADS 5 cross S5 pure spinor superstring. We know that both green Schwarz superstrings and pure spinor superstrings represent integrable, classical integrable models. We know that important progress has been made in order to deform the green Schwarz superstring in ADS5 cross S5 while preserving classical integrability and kappa symmetry. However, few examples of deformations on the pure spinor side are known. So in this work, we present an integrable deformation of the pure spinor superstring in ADS 5 cross S5. This deformed model preserve all the local symmetries of the theory. So I mean BRST invariance and local Lorentz symmetry, which is important. The most important result of this deformation is that this deformed model describes an eta deformed background. Okay, so in order to better understand the eta deformations, we will start by reviewing some important facts about the eta deformation in the Green-Schwarz model. So it's very well known that superstring in ADS5 cross S5 can be formulated in as a super coset sigma model. This super coset model, the superalgebra associated to this super group possess an automorphism of order 4. This allows us to decompose the algebra in 4 sectors. In that sense, the Morecartan forms can be decomposed in the same way. So, the classical action of the Green-Schwarz superstring, it is written in terms of the Morecartan forms. It has this phase. Well, we can introduce some linear combination of projectors on the subspaces of the algebra. In that sense, we can write the action in a shorter way, and this action presents the well-known kappa symmetry, and it was also shown that this action, the classical equations of motion of this action can be cast in lax representation. So preserving, showing that this action is classical integrability. So classical integrable. Sorry. Okay. The Jan-Baxter deformation of that model was described by Delduc, Magron, Bicedo. This kind of deformation, the ingredient of this deformation is a linear operator which is called the R matrix, which solves the modified classical Jan-Baxter equation. The important fact of this deformation is that it preserves classical integrability and also kappa symmetry. Okay. What it was surprising about this model is that the background fields that are produced by this deformation, they are in general do not satisfy the type 2b supergravity equations of motion, but rather a generalization of this. This generalization present a pair of scalar, a pair of vector fields instead of the gradient of the dilaton. So, in that sense, we can understand this model as we can understand the type 2b supergravity as a subsector of this equation of motion. For the special case in which the vector field is equal to the gradient of the dilaton. So, in the language of the eta deformation, in particular, for the eta deformation, this supergravity constraint or this supergravity condition can be written in a relation can be translated in this relation on the R matrices, which are called the unimodular condition. So for this kind of R matrices, the deformation produce a supergravity target space. So now we can talk about the pure spinor. Okay. The most general action which in 2 dimensions which preserve BRST invariance and is classical and also presents classical conformal invariance was written by Berkowitz and Howe. This is the most general BRST pure spinor action in a general background. To preserve the correct number of degrees of freedom, it is also required that this action is BRST invariant, but also we need to require that the nilpotency of the BRST charge and also the holomorphicity of the BRST currents. The proposal is that imposing those constraints, it is sufficient to obtain a supergravity background. This was the claim of Berkowitz and Howe. So, in that sense, a nilpotent BRST charge and holomorphicity BRST currents should imply supergravity, on-shell supergravity. Okay, so and now we can study the pure spinor superstring ADF phi cross phi. This is the action of pure spinor superstring ADS cross phi. It presents okay, we can see 3 sectors. We have one sector. I'm sorry. We have one sector. Sorry. We have one matter sector. Matter sector depends only on the Morel-Cartan forms. We have some coupling sector, which, okay, as I say, it couples the Gauss sector and the matter sector, and we also have a pure spinor, a pure Gauss sector. This Gauss, these are the omega and lambda Gauss. The lambda Gauss are known as the pure spinor Gauss. They satisfy the pure spinor condition. And this action is invariant under this BRST transformation. It was proven by Valillo that the equations of motion of this action can be cast in a in a zero curvature condition while defining a lax pair. So this model presents the property of classical integrability. So what is this is the main idea of this talk. So as I said, there are few examples of consistent deformation for the ADS 5x5 impure spinor, but a remarkable approach was given by Bedoya, Bevilacqua, Mikhailov, and Reveles. And this work, they developed some mechanisms in order to deform this model in a very BRST invariant way. So, in that sense, we can think about this deformation that the action and the BRST charge can be deformed as a polynomial expansion in some parameter, some deformation parameter, and the coefficients of this expansion can be fixed by solving the last equation, which is the imposing BRST invariant. So this equation, those equations, this equation has to be solved order by order in eta. So for example, at order 0, we have the definition of the BRST charge undeformed acting on the action undeformed. So this has to be 0 by definition. And to the first ordering in eta, we have to in that sense, for example, we know that we know the undeformed action, we know the Q0 action of the BRST action. So we need to solve this equation for Q1. So we need to know the value of V1. So what is this V1? So what is the idea to deform this model? So in this approach, the idea is to considering this a massless vertex operator, this is a physical state of the model, we look for a deformation of this state, and the deformation which is related to this vertex operator is the integrated vertex operator. So this is given by V12. So including this V12, including this V1 in the second equation, it is possible to solve Q1, and so on. These equations has to be solved order by order. So this is the main idea to deform the action in a very RST invariant way. So it is possible to do well. We have done this deformation, and it is possible to write the full deformation of the model in that sense. This is the first equation. In the first equation, I present the action, the full deformed action. It, as the original model, it presents one matter sector, one coupling sector, and one Gauss sector. Sorry. And also, it is and this action must be invariant, and the BRC transformation given with those equations. So I forgot to say this deformation, these vertex operators are parameterized by uh, te a tensor, a tensor which I call as B. So this is the same B that appears in in the action and on the VRST transformation. Uh, so we need to prove the consistency of this construction. So first of all, we have to prove the nilpotency of this VRST charge. So the nilpotency of the VRST charge requires that this B matrix actually is an R matrix. So this B matrix must satisfy the modified classical Jan-Baxter equation to have a VRST charge nilpotent. So in that sense, we have a Jan-Baxter deformation as a requirement for VRST invariance. So, okay, but an important feature of this deformation is that not all the vertex operator that we have defined in the first equation, not all these vertex operator represents non-trivial states. There are a family of states for ones that B is given by this relation. B of V is equal to F IVC AC. For these states, this vertex operator is a trivial state. So this trivial state represents some. This trivial vertex operator represents some states that does not appear in the supergravity spectrum. They is transformed in the joint representation, and in that sense, they are not physical states, but they produce a well-defined deformation. So this is an important property that we have to keep in mind. Well, so in principle, this kind of deformation should produce some target background that is not fixed to, is not forced to represent a supergravity background. So what is happening here? So the main well, this problem can be understood when we study the conformal invariance of this kind of states. So those states are only primary fields when the unimodular condition is satisfied in that case. So we can, in that sense, in the pure spinor model, in the pure spinor deformation, the unimodular condition appears as a consequence of conformal invariance. Okay. Once we have constructed, once we know that we have a Jan-Baxter deformation of the pure spinor model, it is possible to rewrite the equations of motion of this model, which is a very ugly model, but the equations of motion can be put in the we can show that the equations of motion present the same structure of the undeformed equation of motion, but exchanging these deformed currents, which I defined as cursive J, changing these currents by the undeformed Morey-Cartan forms. So in that sense, the equations of motion present the same structure, and as a consequence, the model represents a classical integrable model. It is possible to construct a lax sphere representation. Okay. As I said, and also it is possible to show using the equations of motion that the VRST density charge, the VRST currents, they are also holomorphic and anti-holomorphic, as Berkowitz and Howe propose. So, so the last part of this work will be to read the target space fields of this deformation. So what is the plan to the plan to read the target space fields is comparing the deformed eta model, the eta the eta pure spinor model with the Berkowitz-Howe action, which is the most general action for a superstring in the general background. So by doing this, we can do this by assuming that the deformed geometry of the pure spinor deformation represents the same geometry of the Green-Schwarz deformation. So we assume that the super Willweins of the Green-Schwarz model are the same than that the Willweins that appears in the eta deformation. So assuming that this is true, we can read all the background fields. For example, we can read the metric, which appears here. Also, we can read the B field. And also, I have written the Ramon B spinor, which appears also in the pure spinor action. So, what is important about this result is that those deformed fields are the same fields that has been obtained in the eta deformed model for the Green-Schwarz. So in that sense, we have construct a consistent deformation of the pure spinor model, which represents a superstring moving on eta deformed background. So of course it has some consequence. Well, as I would like to finish this talk saying that, well, telling some important ideas or some important facts that should be understood better. For example, the proposal of Berkowitz and Howe was that pure spinor superstring only should be defined on a supergravity background. So we have proof in that sense that it is possible to construct pure spinor superstring in an extended supergravity background. So an important, well, it will be very interesting to understand what is happening in this scenario, and how can we generalize this construction of Berkowitz and Howe? How can we understand better this construction in order to obtain supergravity, extended supergravity from this from that model? So in that sense, we expect that this action, this model is scale invariant. We have calculate the beta function of this model at one loop, and we have showed that this model is scale invariant. But there are some problems. There should be some problems with Weyl invariance. So we expect that Weyl invariance, as for the Green-Schwarz model, should be preserved only for for supergravity backgrounds. So that's what I wanted to talk.